Welcome in. This is a pretty decent challenge for a first year calculus student. So I remember receiving this question on my first year calculus exam, and I got the answer right, but I didn't do it through calculus. I basically just kind of guessed because I remembered the optimization of various figures. So I got zero. Now, I basically wanted to show you this example, and let's see if you can solve this. Now, you can, of course, pause the video and take a look and see if you can do it on your own. So the main idea is that you've been given a ladder. So you have this ladder standing against the wall. It makes basically a triangle, as you can see there, if it's standing against the wall right there. That ladder, we don't know what the height is. We just know that it's of height h. And you are asked to place the ladder in such a way that it maximizes the area which the ladder makes with the wall itself. So basically this problem boils down to kind of the following. So you are kind of creating this triangle that you have in here, and this triangle you're trying to maximize this area right here. So now we know that the area of a triangle is just 1/2 base times height. Now the height right here, so that is, going up in this direction. All right, so I'll assume that that is the height. The ladder itself, okay, I'll put capital H. That's what they have used in the question in here. So you'll see that. And then the base, we can assume is this. So now we want to be able to have our angle, okay, which is this angle, when it tries to maximize the area that is actually made there. Okay, so how would we go about doing this when we have nothing else and we're supposed to use calculus, and supposedly we've gone through, okay, our calculus course and we're finishing up here? Well, you have to kind of trace back and think of all the things you've learned about triangles and then about maximizing. So you are going to be doing quite a bit of work if you want to try to show the full steps of showing exactly what that angle is. So let's take a look. Now, of course, this area can be rewritten. Now, what I'm going to do is, the base times height. Right there, I know that the base, so because I have chosen theta as my angle, you can put it as x. It doesn't really matter what you choose as that variable. And I'm going to work with degrees, I guess, but it doesn't matter again. You can work with radians if you wanted to. So that base is nothing else but simply h multiplied by cos theta, right? That's just from our triangles and then the definition of our actual angles that we have in there. And then our height, h, is nothing else but h times sine theta. So we have those two, and once we have that information, I can simply just substitute it back in here. So what I'm going to get is, now notice the h and the h, so it's going to become h squared right there, and then it's multiplying the sine and the cos together. So I guess you have sine theta multiplied by cos theta, or vice versa, okay, base times height. So that is my area. Now, this area is dependent on the actual angle, right? So this area really is a function of theta. And now if I massage this out, I'm going to just kind of show you what I want to do. This right here, I'm going to use an identity. So this actually is an identity with regards to just recalling, kind of the double angle or the compound angle, which, you so often utilize with trig. So sine theta cos theta is nothing else but simply 1/2 times 2 sine theta cos theta. All right, so I just wanted to put that half and the 2 because they cancel with each other, and the reason why I'm doing that is because I want this 2 sine theta cos theta is that double angle or the compound angle. Okay, this is nothing else but just simply sine 2 theta. So my area is, if I bring everything together, is going to be this. h squared over 4 sine 2 theta, and my area is dependent on the angle. All right, so that is what I have so far. Great. Now, in terms of maximizing, right, or even if you had minimizing, then we know by calculus we can just take the derivative, right? So if we take the derivative and we set it equal to 0, we can find our critical points, and those critical points can be our local maximums or minimums. In this case, we're looking for a maximum. So I can take the derivative of this with regards to theta, right, with regards to the angle. Now, this angle, of course, cannot be, it's kind of outside of this range. So let me just be careful in here. So I'm going to put this in degrees. Now, of course, it can't be 0 because then the ladder is just flat, right? So then there's no area at all. And it can't be 90 degrees, okay, within here. So if you, make it upright, that's basically right against the wall. And again, you do not have any area. So it has to be between that range somewhere. All right, so that's good to know. Now, if I take the derivative of this, so this is, let's say the first derivative with respect to theta, it's going to give me, this is just a constant, so nothing happens there. The derivative of sine is just cos, so this is going to be cos 2 theta, and then of course this is a chain, so you're going to have times 2 because of the argument, the 2 theta in there. And this whole thing, so h squared, I guess this is going to be now 2 because this will cancel that off, and then this is just cos 2 theta. I think you can see where I'm going with this. Now, I have to set this equal to 0 because I want to find out the critical points. Well, if I set this to 0, then this stuff is actually irrelevant, right? Because it's just a constant. Now, h is not 0. So, if we bring it over and divide it, okay, it's going to be gone. So really what I'm looking for is I'm looking for cos 2 theta. Where is it equal to 0? Well, that shouldn't be too difficult. So if you, recall, so this 2 theta right here, where is cos, okay, equal to 0? And again, you can kind of go back and think if you've forgotten, your unit circle. We're just working in the unit circle with regards to between 0, all right, and 90. So we're kind of going between here and here. That's where we want the theta to be. But when is, cos equal to 0? Well, cos is equal to 0 right here, and it's equal to 0 right there. So it's at 90 and at 270 and any replication of it. Now, we don't need that because our ladder it's not going to be swinging around there. So within here, really the only two choices, okay, that I have is 90 and 270, and 270 doesn't really work for me, again, because of the way that the ladder is positioned. So that is telling me that this 2 theta has to be equal to 90 degrees in order for cos to be equal to 0. Well, of course, now dividing by 2, you're going to find out that theta must be 45 degrees. And that is the angle that we were looking for. Now, again, this shouldn't really surprise you because if you have a triangle and you're trying to maximize the area, it is going to be an angle which is basically an equal lateral kind of triangle. So you have 90 degrees set in, okay, and then 45 degrees. So it's an isosceles kind of triangle with the 45 degrees there that we have in. Now, with this 45, this should do the trick, right? You should say, okay, so the angle is 45. Now, again, because maybe it's an exam and they're really picky, you might want to kind of show that indeed this happens as a maximum. It's not like a minimum or something, although minimum wouldn't really make sense in terms of areas in here. But hey, if they really push you for that, then don't forget that you can use, concave up and concave down concept. So, taking your derivative, so our derivative was h squared over 2 cos 2 theta. If you take the second derivative right there, then what you're going to get is h squared 2. This is going to be now negative sine 2 theta, again, times 2. So, this this 2 and this 2 will cancel. Not that it will matter for us, but anyways. So this is h squared. The negative can come out, and then you have sine 2 theta. This is your second derivative. And what do we know from the second derivative? Well, we know, okay, if our functions, okay, if there were a function, in this case, I guess it's an area function with regards to our theta, if it's concave up or concave down. So if I substitute the 45 in here, well, then what you're going to get is negative h squared. And then sine of 45 is really just sine of 90. And sine of 90 is nothing else but 1. So this equals to negative h squared, which is always less than 0, right? Because our height of the ladder, we're assuming that it's not 0. So it's some positive value, and then it's squared. So this is always negative, which means, again, so in terms of concave up, concave down, this must be concave down, and that is a maximum at 45 degrees. And there you have it. So now you have proven and solved this fun question from a calculus problem from first year. All right, so happy studying. I hope that you found this useful, and let me know down below if you were actually able to solve this without kind of guessing and using calculus to prove your result. All right, cheers everybody. Bye.